السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا. كل عام وأنتم بخير بمناسبة شهر رمضان الكريم. أعاد الله علينا وعليكم الخير والبركات. استكمالا لشابتر 8 اللي بدينا فيه المرة الماضية، واللي هو كان عبارة عن flow inside or internal convection heat transfer، واللي هو بيحصل دائما أو عادة داخل التيوبس or ducts. Okay. So شرط هذا النوع من الفلو إنه يكون الفلو bonded from all direction. ووصلنا لهذا السلايد. حكينا في السلايد السابقة إيش أسماء regions in terms of thermal or in terms of velocity. Okay. وشوفنا ال thermal entrance length وال hydrodynamic entrance length، وشوفنا لكل الحالات للturbulent ولللامينر. Okay. Now the general thermal analysis, the rate of heat transfer for steady flow of a fluid in a tube. خلينا بس نشوف القلم. So here we have a flow, okay, inside this pipe. Okay, so this is the direction of the flow, and you know very well that the flow is entering with certain temperature, T inlet, and this T inlet is not ordinary temperature, it is the mean inlet temperature, and it left the pipe with T exit, and this exit again is mean temperature. Okay. So the heat transfer, the rate of heat transfer to the flow is equal to Q dot equal M dot CB T exit minus T inlet. Okay. So this is the amount of energy that is transferred to the fluid flowing in the tube. Okay. But this Q dot, from where it comes? This one. Here is the question. Is it due to condensation outside, evaporation outside? Is it due to coils, heater coils? Okay. What is the reason of this dot? Why the temperature T exit, for example, in this scenario, T exit is larger than T inlet? Okay, so we'll ask ourselves this question. Where Tn and T exit are the mean, this is very important, fluid temperature at the inlet and at the exit of the tube. The thermal condition, so this Q dot, we call it thermal condition. Okay, the thermal condition at the surface can be approximated to be constant surface heat flux, constant surface temperature, T surface equal to constant, or constant surface heat flux. So either we said that the surface of the tube is at constant temperature, okay, Ts is equal to constant, or Q dot S is equal to constant surface heat flux. Okay, either this scenario or that scenario. So from here the heat transfer to the flow, and the flow temperature is rising. So the constant surface temperature، لما بنحكي إنه ال surface temperature للبايب remain constant, it means, or it resulted from, this condition is realized when a phase change process such as boiling or condensation occurs at the outer surface of the tube. كيف ممكن أحافظ على درجة حرارة ثابتة على السطح؟ By phase change. Okay, by phase change, either boiling or condensation. And that does not mean إذا كانت Ts is equal to constant, that does not mean Q dot S is equal to constant. Okay, so if Ts is equal to constant, it means Q dot S is increasing. Okay, and if the Q dot S is constant, that does mean Ts is increasing. Okay, so if one happens, that does not mean the other will occur. Constant surface heat flux, when this scenario happens, is realized when the tube is subjected to radiation or electrical resistance heating uniformly from all directions. Yeah, and usually this is the case, electrical resistance heating. So we have certain coil, okay, and this coil is at constant surface heat flux, okay, but the temperature will increase rapidly with this scenario. Ts will increase when we have constant heat flux, okay, and here when we have constant surface temperature, Q dot S will increase. And you know very well that the surface heat flux that comes from, for example, electrical resistance is equal to H local multiplied by Ts minus T mean. Okay, where Hx is the local heat transfer coefficient, Ts and T mean are surface and the mean fluid temperature at that location. Okay, so if we are talking about this location, Q S entering this location is equal to H for this location because H keeps varying if we are in the entrance region. If we are in the fully developed region, H become constant. Ts minus T mean, okay, for this location. Okay. Let's start with the first scenario, constant surface heat flux, Qs is equal to constant. Here in this example, we have this tube. We have flow N with the inlet. Of course, you noticed earlier that we did not write here T inlet mean, T exit mean. So whenever you saw these symbols, T exit, T inlet, that means we have mean inlet, mean exit. Okay, so we drop the symbol N. So, and here we have T exit, T mean exit, and you can tell easily from those arrows that we have constant heat flux. Okay, this is an indication. If you have these arrows from two directions, that means we have constant heat flux. Okay, now here is the profile for temperature in the y-axis, and in the x-axis the length of the tube. Okay, and its length is L. So from 0 to L. From 0 to L, the fluid temperature inside the curve is in blue color, and the surface temperature of the tube is in black color. Okay. Now, why the curve of the fluid temperature profile is linear? Why is it is linear? Okay. It starts from temperature T inlet, the temperature of the inlet fluid, mean inlet temperature, and it exits with the T exit mean. But the profile is constant. Okay. Here you can also see that we have two regions, entrance region, and here we have fully developed region. Another question, why Ts is varying at the entrance and then it is remain linear beyond the entrance, okay, in the fully developed region. Why? To answer those questions, let us see the following equations. The rate of heat transfer Q dot to the fluid is equal to the amount of heat flux entering the tube. So the Q dot is equal to Q dot rate of heat transfer entering the tube is equal to m dot Cp T exit minus T in. Okay, amount of heat entering the tube. and this amount is equal to amount of heat flux entering the tube. So Qs multiplied by S, and we agree that Qs is equal to H Ts minus T mean. Okay, you can add here X. Okay, so the mean fluid temperature at the tube exit. So if I just rearrange this equation, and I want to tell you something after rearranging. Okay, so here it is. We divide this equation by m dot cv both sides. M dot cv. So this cancel with this one. So here it is. And we transfer T inlet to the other side to become positive. So T exit is equal to T inlet plus Q dot S AS divided by M dot CB. Now, why the blue profile is linear? Because of this equation. Okay, this is the equation describe what happens to this profile. This profile. Okay, T inlet mean is constant, and here it is, specified temperature. The fluid entering the tube with known temperature. Now, Q dot S is constant. Here it is. Qs is constant. This is the first scenario. Surface area, we are talking about constant bar diameter. Okay, so surface area, which is 2 by R multiplied by L, is constant. R is constant, length is constant. M dot, again, is constant. We have certain mass flow rate. CB, here usually I told you before that this is the average value, okay? But usually we drop it. So this term again is constant. So actually, if we have a flow temperature of 20 and we add to it 50, then we end up with 70, which is a specified temperature. So the T exit will be 70. So if we have inlet 20 and the exit is 70, then this profile is linear. And which equation describes its linearity? This equation. Okay? This equation. Surface temperature. So here we have a Qs, okay, which is equal to H Ts minus T mean. I'm looking to T surface, this profile, okay. So this profile is best described by this equation. Okay, so just rearrange it, divide by H, both sides. This will cancel out and transfer this one to the other side. So you end up with Ts equal to T mean plus Qs over H. Okay. Now Qs is constant. H, it could be variable, it could be constant. It is variable in the entrance region, okay, as we saw earlier. Here, for example. So it is variable in the entrance region, but it is constant in the fully developed region. Okay, this is why this profile is constant or linear in the fully developed region, okay, because of H, and in the entrance region it is variable. Okay. Now regarding T-mean again is constant. Why? Because this profile represents the T-mean at any location. Okay. T-mean. Here is T-mean at the inlet, T-mean at the exit, and here T-mean at any location. Okay. So if we are talking about entrance or fully developed region, it is the same. So this term remains constant, as well as Q dot S. The only variable is H. So in fully developed region, fully developed region, this region. Okay, this one. The surface temperature will also increase linearly in the flow direction since H is constant. So this is the main reason. And thus Ts minus T mean is equal to constant. So this value, Ts minus T mean, is equal to Q dot S over H, which is equal to constant value. Okay. So Ts minus T mean, this profile we call it S, this profile we call it T mean. So the subtraction is equal to constant value. So always this distance remain constant between, so they are parallel profiles. Okay, the difference between them is remain constant. Okay. Now let's take a portion of the fluid. Okay, only small portion. So what will happen to this equation? This term will be affected, and also this term will be affected. Here it is. So Q surface multiplied by area surface. Since we are talking about very small portion, then the area surface is not the whole pipe, it is only small portion, which is the parameter of this portion multiplied by the length of this portion. Okay, this portion, its length is delta x, and the parameter remain as is, which is 2 pi r. Okay, m dot, amount of flow rate entering, Cv multiplied by change in the temperature of this portion. So it enters with T mean and it exits with T mean plus delta Tm. So if I subtract the exit minus the inlet, so T mean will cancel with T mean and we end up with delta T mean. Okay, so here is the equation. So you subtract this value from this value. Okay, m dot Cv is common factor, and T mean here cancel out with this one. So we end up with this equation, with this portion. Rearrange this equation by dividing both sides with delta x. Okay, so delta x here. So it will cancel out. And divide again by m dot Cv. So here is m dot Cv. So this will cancel out with this one. So we end up with delta Tm by delta x, this one, is equal to Q dot S multiplied by parameter divided by m dot divided by Cv. And all of these variables are, as we agreed in the last slides, they are constants. Okay, where V is the parameter of the tube, which is 2 pi r. Okay. And this result also similar to the previous results, where the slope is equal to constant value. Okay, so this is the same. Now the other equation, but T surface equal T mean from the heat flux equation, which says that Q dot S is equal to H local or H multiplied by Ts minus T mean. Just rearrange it in terms of Ts. It will be look like this. Take the derivative with respect to x, both sides. So this term is constant, as we mentioned. Now we are talking about fully developed region, okay? And here it is. We are talking about fully developed region, okay? Fully developed region. So they are the same. So once we are in the flow developed region, that means this term with respect to x is equal to 0. Okay, and we end up with d delta tm divided by delta x is equal to d ds divided by dx, and this is must equal to the previous result. Okay, q dot s multiplied by parameter divided by n dot cb. Also, the requirement that the dimensionless temperature profile remain unchanged in the fully developed region. This profile remain unchanged, remain constant. Okay, which says that we saw this relation actually earlier when we talked about that this T in the fully developed region remain unchanged. Remember? Okay, so if I derive it with respect to x, so the temperature here is variable only with R. Okay, now if I derive it with respect to x, the other parameter, because temperature depends on two variables, the length x and the radius r. This is why here we saw differential. Okay, so if I take the derivative of this dimensionless temperature profile, so this term is constant with respect to x, because we are talking about fully developed region, change remain constant, and we end up with delta or partial differential of ts minus partial differential of delta t. Okay, so this term vanishes with the 0, and we end up with delta t at any location, okay, equal to dt over dx. Okay, so this partial become constant, okay, because the surface temperature has only one variable, which is the length. Okay, so if I combine this result with this result, we'll end up with partial t by partial x equal to first derivative of ts, first derivative of tm, and it's equal to q dot s multiplied by parameter divided by m dot c equal to constant amount. So if we are talking about circular cross section, so parameter is equal to 2 by r, m dot equal rho v average cross section area, and it is by r squared. So if you substitute, you will end up with this amount. Okay, so this is if I ask you to find the temperature variation with respect to x in terms of temperature of the flow, temperature of the surface, or the mean temperature of the flow. Okay, so from the constant surface temperature, what I need this result, the final result. Okay, and I need those results along with this profile. So if I ask you to draw the profile for constant heat flux, you will be able to justify why this is linear, why this one is non-linear in this region, and it becomes linear. Okay, so the other scenario is constant surface temperature. Ts is equal to constant. The rate of heat transfer to or from fluid flowing in a tube is equal to, so Q dot entering or gained by the flowing fluid is equal to heat flux, as we agree. Okay, so this is H multiplied by AS multiplied by delta T averaged, and this delta T average is equal to TS minus T mean averaged. But this scenario is not acceptable. This delta V averaged, delta T averaged, we cannot write it like this. Okay, in this scenario. What is the best way to write it? So we have two suitable ways of expressing delta T averaged. Either we'll benefit from arithmetic mean temperature difference, delta T arithmetic mean. So A represent arithmetic and M represent mean. So temperature difference, arithmetic mean. So arithmetic mean, temperature difference. Here the same. Log mean temperature difference. Okay. So either we'll benefit from this scenario or that scenario in order to substitute it inside here. So this equation using this scenario becomes U dot equal H multiplied by surface area multiplied by delta T arithmetic mean, and in this scenario U dot is equal to H AS delta T log mean. So in the problem statement, either I'll tell you to use this one or use this one. Okay. So let's start with the first one, arithmetic mean temperature difference. So delta T averaged is almost equal to delta arithmetic mean. So the scenario that we refused at the beginning, okay, we reject it and we'll use instead of it the arithmetic mean, which is equal to delta T inlet plus delta T exit divided by 2. Okay, and delta T inlet, this is very important to memorize, okay guys. So delta T exit or inlet is equal to T surface minus T inlet, and delta T exit is equal to T surface minus T exit. Okay, so here we have 2Ts, and it's divided by 2, so 2 will cancel out, we'll end up with Ts minus, so I take minus as a common factor, T inlet plus T exit over 2. If you remember, when we start this chapter, we call this amount as the T bulk. Okay, remember? So we call it T bulk. So delta T arithmetic mean is equal to T surface minus T bulk. Now, I'll go back to the previous slide. So, and here instead of delta T arithmetic, so this is H multiplied by S multiplied by Ts minus T bulk. This is if we have surface constant temperature. By using the arithmetic mean temperature difference, we assume that the mean fluid temperature varies linearly along the tube, which is hardly ever the case when Ts is equal to constant. So if I wish to draw the length of the pipe on the x-axis, which is vary from x to L, and on the y-axis I wish to write the temperature. So here in this scenario Ts is constant على عكس لما يكون Q this is equal to constant حكينا هيكون variable بعدين linear. Now this scenario the fluid temperature وكأننا بنيجي بنحكي إنه البروفايل لها linear. So this is T inlet linear profile. So we assume that the mean fluid temperature هذه يمثل T mean profile للفلويد وهذا يمثل السطح اللي هو حالتنا هذه constant. We assume that the mean fluid temperature varies linearly along the tube وهذا الفرض يعني بعملنا نسبة error عالية. which is hardly ever the case when Ts is equal to constant. Okay, لما Ts is equal to constant temperature mean temperature profile للفلويد مستحيل يكون linear. Okay. This simple approximation often gives acceptable results but not always. Okay. So هي تعطينا good indication ولكن هذا indication with margin of error, huge margin of error. طيب, which is correct? The correct scenario is to use log mean temperature difference. And take a look here. Here is the temperature at the surface. Ts is equal to constant. And instead of having linear profile, شوفوا مقدار الإيرور, we'll benefit from the log mean temperature difference. So instead of having this difference, Ts minus T mean, with logarithmic mean temperature, we have only this difference between the values. Okay, so here T inlet, and here we have T exit, and the surface temperature is constant. So in order to derive the equation, I'll show you the final format of this equation. So Q is equal to HAS. Instead of delta T average, I'll use delta T log mean. And this delta T log mean is equal to this equation or this one. So you can use either one of them. So I used to bring to my students this format, but they need to keep in their mind. So هذه المعادلة ما بطلب عادة حفظها, ولكن إيش بجيب هذه المعادلة. What you need to know that delta T exit is equal to Ts minus T exit, and delta T inlet is equal to Ts minus T inlet. So you need to memorize again those quantity. Okay. So yeah, we benefit from this equation. But how this equation derived? From here. We come and say Q dot for the fluid is equal to Qs multiplied by As. If we are talking about the small portion, then it will be delta As, and this is delta T mean. Delta As is equal to parameter multiplied by dx, and instead of writing delta T mean, I'll write Ts minus T mean with minus sign, assumption. So substitute this one inside there. Okay, we'll end up with this equation. So this equation, we can divide both sides by Ts minus T mean, both sides. And here instead of delta Tm, we have Ts minus T exit, okay, or Ts minus T mean, this equation. And here is the minus sign. And we divide both sides by m dot Cb, so we move this one to the other side. We have h multiplied by parameter divided by m dot Cb dx. So this equation will integrate it from x0 until the whole length of the pipe, and here we have integration and its limit between t n up to t exit. T mean exit. Okay, so if you derive it, you will end up with this equation. If you need to calculate T exit alone, so take the exponential for both sides, and you will end up with this equation. Okay, so T exit is equal to T surface minus T exit multiplied by exponential to the power minus HAS m dot Cb. This power, we call it, without minus sign of course, NTU, number of transfer units. And this is very important number. Okay, this is very important number. So here it is. HAS divided by m dot Cb, we call it NTU, and here is the range of this number based on this experiment. Okay, here what do we have in this experiment? We have T inlet at 20 degrees Celsius, and I wish that the T exit, its temperature to be 100 degrees Celsius. Okay? Why? Because when I apply constant surface temperature 100, then I need the fluid flowing inside this tube to reach this temperature. This is my target. Okay? So when this happen, here is the T exit. When this happen, so here it reach 100, the surface temperature. So my target is achieved when NTU is equal to 10, number of transfer unit. And number of transfer unit, it consists of four parameters: H, AS, M dot, CB. Okay, so I need certain flow rate. Okay, I need certain H. Okay, and I need certain surface area. So in practical، يعني لو افترضنا إنه هذا السؤال practical الحياة العملية، بيجي واحد بيحكي لك أنا بدي تحكي لي كم طول البايب اللي لازمني. okay. إذا أنا حكيت لك أنا بدي مثلا بايب 1 inch okay. or 2 inch وبدي الحرارة، يعني هذه المعطيات اللي أنا مزودك فيها. عندي ال inlet temperature profile 20 وحابب يكون ال exit temperature profile 100. so وعندي مصدر حرارة خارجي بزودك بsurface temperature 100. okay. so كل هذه المعطيات، واللي أنا بدي إياه منك تحسب لي طول البايب L. L is the only unknown. So how you can achieve it? You come to here, you select 10, and then this is the temperature that you want. okay. ولكن هذه إيش بتكون؟ تكون على حساب، طبعا قبل لا هيك كل الانونز الثانية بتكون given، يعني ال H بتكون محسوبة لك سواء كان natural ولا forced ولا boiling. okay. so كلها بتكون محسوبة. M dot كمان given, CB given, assumed. okay. so we end up with this surface temperature. so surface temperature إيش بيساوي؟ 2 by radius of this tube multiplied by L, and L is the only unknown. كمان شوي حنشوف كيف حنحسب هذا السؤال. بس السؤال اللي بيطرح نفسه، هل إذا رحت أنا a little bit lower with this NTU هيعطيني result unacceptable؟ so إذا رحت مثلا ل5 هيعطيني T exit is equal to 99.5 which is again still acceptable. okay. so as engineer إحنا عادة ما بنفضل نروح لل10 لأنه عشان أحقق أنا 100 degree Celsius حيكون هذا على حساب الكوست. okay. so دائما بنروح على compromise solution. لا الحرارة كثير عالية مثلا هذا الحل، still هذا الحل كمان acceptable. okay. لا أنا حدفع فلوس كثير. okay. فلوس كثير in terms of what? in terms of pipe length. okay. لأنه حنشوف كمان شوي كل ما كان الرقم قليل كل ما كان اللينث للبايب قليل. okay. لأنه تناسب طردي مع ال NTU. okay. ولكن إذا كان ال NTU كبير معناته اللينث للبايب حيكون كبير، بالتالي حدفع أنا فلوس أكثر عشان أجيب بايب طوله أكثر. okay. so it depends. هل أنا عندي سماحية إن أروح لل70؟ هل الابليكيشن اللي أنا بستعمله عادي لو طلعت عندي التي اكزت 70، ولا أنا الابليكيشن عندي very critical I need 100. so it depends on the application itself. okay. so here in the caption it says what? An NTU greater than 5 indicates that the fluid flowing in a tube would reach the surface temperature at the exit regardless the inlet temperature. okay. so up to here we reach the target, we achieve the target. Beyond this value still we are far away from the target. So NTU is number of transfer units, and it is a measure of the effectiveness of the heat transfer system. So ال NTU لو كانت unknown وحسبتها وطلعت قيمة جدا عالية معناته أنا عندي السيستم very effective. For NTU equal to 5, T exit is equal to T surface almost, because we are talking about 99.5. And the limit for heat transfer is reached. A small value, whereas a small value of NTU indicates more opportunity for heat transfer. So مثلا أنا لو وصلت عند 10 وطلعت عندي الحرارة 100، كان طول البايب مثلا 100 متر، وحصل مثلا لو أنا هذا الطول 100 متر 100 متر، وصار إنه التي إكزت أو التي للفلويد على هذا الجزئية على هذا اللوكيشن إكس مثلا نوت، وصلت عندي الحرارة تي مين equal 100. هل إذا بكمل أنا بالفلو inside this tube وبعرض هذا السيرفس ل 100 constant surface temperature، هل حيكون في عندي انتقال حرارة للداخل؟ لا، رايحة تتوقف. ليه؟ لأنه المين temperature مش رايحة تزيد أكثر من 100، لأن هي already وصلت 100 عند هذا اللوكيشن. تمام؟ هذا معنات ال 100 here. ولكن إذا بروح عند أي رقم ثاني مثلا 0.5، T exit is equal to 51.5. لو رحت وطولت البايب كمان still في عندي opportunity إنه الهيت still entering the tube. Okay, so هذه معنات الجملة هذه. A small value of NTU، small value يحكي عن هذول ال values. Okay, up to here. Even this one، بس هذه with a small fraction. A small value of NTU indicates more opportunities for heat transfer, and heat transfer continues to increase as the length is increased. Okay. لأنه الحرارة ما راح تتوقف، إحنا still ما وصلنا للمية. متى بتتوقف انتقال الحرارة؟ إذا أنا وصلت المين exit temperature 100. أوكي. So هذول هم المعادلات اللي لازم تتذكروهم في حالة استعملتوا اللوج مين temperature difference scenario. أوكي. هذول هم كل المعادلات. خلينا نشوف سؤال. حل هذا السؤال، وحيكون في أسئلة ثانية ممكن أنتوا تحلوها، تروحوا على الكتاب وتحلوها. بس أنا على هذا الشابتر هحل هذا السؤال، حفرجيكم كيف ممكن نستفيد من المعادلة. Okay. In this example, we have a water enters 2.5 centimeter. Let me activate a 2.5 centimeter internal diameter of thin cover tube of a heat exchanger. So here we have heat exchanger, and this heat exchanger consists of thousands of tubes like this tube. Okay, so here we are tackling only one tube. It could be 100, could be 1,000 tubes. Okay, so it depends on the capacity of this heat exchanger. So here we have water enters 2.5 internal diameter thin cover tube of a heat exchanger at 15 degrees Celsius. So this is the entering 15 degrees Celsius at a rate of 0.3 kilogram per second. So this is m dot, and this is the n. Okay, and is heated by steam condensing outside at 100 degrees Celsius, 120 degrees Celsius. So here we have another phase, another substance which is condensed outside. Okay, so here we are talking about constant surface temperature. Okay, because we have phase change. If the average heat transfer coefficient is 800 watt per meter squared Kelvin, okay, and in next chapter we'll come to this value. Okay, how to determine this value also. Okay, it is not straightforward. We need to find it and to determine it. Okay, but here it is given. So if the average heat transfer coefficient, this is average by the way, it is not local. So this is H averaged, or H alone without average. 800 watt per meter degree Kelvin. Determine the length, so we need to find L for this tube, required in order to heat the water to 115. So here is the case. We have water entered at 15 degrees Celsius and we need the exit temperature to be 115. If we apply constant surface temperature 120, so find the required length of this tube. So it is unknown. In order to achieve this one, T inlet temperature, m dot, and H, find L. Okay, and here he said use log mean temperature difference. Let us go to the solving board and try to solve this problem. Okay, so what do we need to do first? I need to write first the equation for log mean temperature difference. So Q dot is equal to H multiplied by surface area multiplied by delta T log mean. Okay, so here for this term we have special equation for it. Okay, I'll use it. And inside this equation we need exit inlet surface temperature and everything is known. So for this term is straightforward. H is given. Surface area is equal to 2 pi multiplied by radius multiplied by L. So in this problem we ask about L. So this is the unknown. R is given. The internal pipe diameter is given. So we can find out radius. Q dot is unknown. But how we can find the Q dot? Q dot is equal to m dot CB T mean inlet minus T mean exit. So T mean exit, sorry, the opposite, minus T mean inlet. Okay, from higher to lower. So here this equal m dot is given, which is 0.3 kilogram per second. Okay. CB for water, you can find it through the tables, either from this book or from thermodynamic tables, which is equal to 4.187 kilojoule per kilogram Kelvin. So this is multiplied by 4.187. Keep in mind it is kilojoule. Multiplied by T exit, which is 115, minus T inlet, which is 15 Celsius. So Celsius with Kelvin, because this is difference, not degree. Okay, it will cancel together. Okay, let me use my calculator. So 115 minus 15 multiplied by 4.187, or the opposite, sorry. 115 minus 15 multiplied by 4.87 multiplied by 0.3, which is equal to 125.61 kilojoule. Okay, per second, because here we are talking about and so I can write, instead of this one, I can write kilowatt. Okay. Now, let me also calculate, so let me name this equation as, this is equation 1, and this equation, the first result is 2. Let me also find delta T log mean, which is equal to delta T exit minus delta T inlet divided by len delta T exit divided by delta T inlet. And this is equal to delta T exit, which is T surface 120 minus T exit, which is 115 mean temperature, minus T inlet, delta T inlet, which is 120 T surface minus T inlet, which is 50, divided by len, the same. I'll repeat the same. So this is 120 minus 15, this is 5, divided by 120 minus 15, this is 105. And if I use my calculator, so delta T log mean is equal to, so len 5 divided by 105, and in the numerator this is 5 minus 105, divide the answer by 9. So the answer is 32.85, and I will name this result as equation. So now we will substitute equation. So substitute equation 3 and 2 and equation 1. So what do we have? We have Q dot. So let me write the equation first. So Q dot is equal to H AS delta T log mean. So Q dot is equal to 125.6 kilowatt, and this is equal H, which is 800, multiplied by surface area. I will not substitute surface area. I will find surface area, then I will find L, multiplied by delta T log mean, which is 32.85. So if I calculate AS, this is equal to, so we have 125.6 multiplied by 10 to the power 3 divided by 800 multiplied by 32.85. 800 multiplied by 32.85, and this is equal to 4.78 meter squared. And this is equal 2 by R multiplied by L. So from here L is equal to 4.78 divided by 2 by multiplied by the diameter, which is for the radius, but we have the diameter, which is 2.5 multiplied by 10 to the minus 2 because it's in centimeter, divided by 2. Okay, so this is equal so 4.78 divided by the diameter, and this gives us 60.89 meter, which is almost equal to 61 meter. So this is the length of this tube in order to achieve the exit temperature 115. So 61 meter, imagine it. Very long pipe. But inside heat exchanger, it will not be will not be installed like this 61 meter in a straight position. It will be a loop. Okay, it will be looped tube. Okay, and the next chapter will learn how the heat exchanger is designed. Okay, so going back to this example, so we finished this example. You can solve any example uh, similar to this one. Okay, and of course this chapter is not ended. There is a lot of information, but I will uh, stop here. That's enough for this chapter, and we'll move to the new chapter. So last chapter, which is chapter 13, talks about heat exchangers. So in this chapter, we'll try our best to achieve these objectives. So we'll start with recognize numerous types of heat exchangers and classify them. Okay, not only one type, we have many types, many classification. Okay, and then at the end we'll tackle and try to do certain calculation for the most famous type. And of course, in the heat transfer lab, you will do one or two experiment on heat exchangers. Develop an awareness of fouling on surfaces and determine the overall heat transfer coefficient for heat exchangers. So we learn what's the meaning of fouling and how it will affect the heat exchangers. Perform a general energy analysis on heat exchangers, and I think we can, with the remaining time, cover these three objectives. Now the other objectives, I'm not sure about it, whether we can finish it or not, but we'll try our level best. So obtain a relation for the logarithmic mean temperature difference for use in LMTD method and modify it for different types of heat exchanger using the correction factor. So we can move from one type to another using the correction factor. Develop relations for effectiveness and analyze heat exchangers when outlet temperature are not known using the effectiveness NTU method. So number of transfer units. Remember the last section of the previous chapter. Know the primary consideration in the selection of heat exchangers. So let's start with the types of heat exchangers. The most famous type is the double pipe heat exchangers, or sometimes they call it concentric heat exchangers. Okay, concentric. Why they call it double pipe or concentric? Because here we have, let me draw it for you, side view. So this is front view. Let us take a look from here. So we'll see something like this. Here is the bigger one, and inside it we have the smallest one. So the one in blue color is this one, and the one in gray color is this one. So this is the one in gray color. So we have one cylinder inside the other bigger cylinder. So we call it either double pipe or we call it concentric heat exchangers. Actually, in this type we have two types of double pipe heat exchanger. Either we have parallel flow, co-current, or counter current. Okay. So the simplest type of heat exchangers consists of two concentric pipes of different diameters as shown in the figure. So why we call it parallel flow here? Here you can see how many inlets. We have one inlet for the cold fluid, and here we have one inlet for the hot fluid. Here we have one exit for the hot fluid, and here we have another exit for the cold fluid. So actually what happens, the cold fluid is flowing and uh, flowing over the hot fluid. Okay, so whenever the cold fluid entering this pipe, okay, it will flow over this internal pipe. Okay. Okay. So وكأنه البايب الداخلي مغمور submerged with the cold fluid. So what happens when the cold fluid uh, cover the hot fluid from outside without mixing? Okay, so this is not mixed. What happens? Heat start to transfer from inside to outside. So the cold fluid start gaining certain uh, certain temperature. So let me here draw for you the temperatures. Uh, sorry, temperature profile versus the length of the pipe. So here we have temperature, and here is the length of the pipe, x. Okay. So here is x equal to 0, for example, and here we have x equal to L. Or let me put it here. So here we have x equal to 0, and here we have x equal to L. So here is 0, and here we have x equal to L. So, and let me draw the temperature profile for the hot flow first. So at the inlet, the hot fluid has maximum temperature. See, so this is T hot N. And what happens when it is flow till the exit? Because some of its heat will distribute it to the surrounding, it will gain by the cold fluid. So it will lost its temperature. So if it starts with 100 degrees Celsius, maybe the exit temperature will be 60. So its temperature will decrease. And the decrement happens like this, as we learned in the previous chapter. It's not linear, it will be logarithmic. So this is the T hot exit. Okay, its temperature will decrease. What happens to the cold fluid? Uh, as I mentioned earlier, that this is the parallel arrangement, okay, parallel flow, because both hot and cold they flow in the same direction. But this counter, okay, because the cold fluid is entering and flowing in this direction, and the hot fluid flowing in this direction. Okay, so they are opposite each other. Now we are talking about this scenario, the parallel scenario. Okay, so the cold fluid entered from this location. So it entered with very low temperature, cold. So this is cold inlet. And what will happen? It will gain temperature, so its temperature will increase logarithmic until it reaches certain value. So this is T cold exit. Okay. So here is the profile. So this profile represents the cold fluid. It enters with very low temperature and it exits with high temperature. Of course, it will not reach the hot fluid temperature because of losses, because of the length of the tubes, many reasons. And the hot fluid, its temperature will decrease from higher to lower. Okay, and you can notice the direction of both fluid in the same direction. Now the counterflow. What do we have? Here we have hot fluid. Okay, it enters with high temperature, as in the previous scenario. Okay, and it exits with lower temperature. So this is the hot exit. But for the cold fluid, here is the entering from x equal to L. So this is the entering, T cold N, and it flows in this direction. Okay, and it exits with this temperature, T cold N. And you can compare between the two scenarios in terms of the efficiency and effectiveness of the two scenarios. Actually, in the lab, we'll do this experiment, and you will tell why the temperature in this scenario is higher than this one. Okay. Okay. Another types of heat exchangers, compact heat exchanger. In the compact heat exchanger, from its name, it has large heat transfer surface area per unit volume. Okay, like car radiator, human lung. Okay. So the ratio of heat transfer surface area of heat exchanger to its volume is called area density beta. Okay, area density beta. A heat exchanger with area density beta greater than 700 meters squared per meter cube, its area divided by, so the ratio between the area and the volume is 700, so beta greater than 700, this value, this amount, we can classify this heat exchanger as compact cross flow. Okay, so the compact heat exchanger come in a classification based on the area density beta. So if it's greater than 700, then this is compact of type cross flow. Okay, as you can see here in the radiator. In compact heat exchanger, the two fluids usually move perpendicular to each other. This is the meaning of cross flow. So if we have flow inside these tubes, we have air come from this direction and flowing to that direction. So we have two fluids perpendicular to each other. The cross flow is further classified as unmixed and mixed flow. Here it is. So this diagram for both fluid unmixed. What do we have here? We have fluid flowing in those tubes in this direction. Okay, and here we have cross flow flowing in these sheets. So here we said that both fluid is unmixed. Whenever we said unmixed, we are we means we mean that the flow itself. So here the flow flowing inside the tubes, flowing inside this tube, it will not mix with the flow flowing in this tube. Okay. The same for the flow come from this direction. The flow entering the first sheet will not mix with the flow entering in the next sheet. Okay. But here in this scenario, one fluid mixed and the other unmixed. The one is unmixed that is flowing inside these tubes. This is unmixed flow. But the other flow, the cross flow, is mixed. Why? Because there is no certain passages for it. Okay, there is no certain passages. It will flow randomly, and the layer come from here will come and mixed with the layer come from other direction. Okay, so we have here random motion. So either mixed or unmixed. So either unmixed for both, or one is mixed and the other is unmixed. The other type is shell and the tube heat exchangers. Okay, so do you know what? I will delay this type of heat exchanger until next lecture. Okay, and until then, stay safe and see you soon.